Let's look at another limit process called a Riemann sum, named after Bernard Riemann, who was a mathematician in the mid 1800s, who did a lot of foundational work in calculus in a branch of math called analysis. Um, as a side note, Riemann is maybe most famous, at least currently, for his function called the Riemann zeta function. And I highly recommend checking out, go to YouTube and check out um, many of the like myriad videos that are out there about this incredibly famous and important open problem in math. It's one of the millennium problems, which if you are the person to solve them, one of the institutes called the Clay Institute has a $1 million prize for whoever publishes a actual proof or counterexample of that thing. So the Riemann function is a super famous problem in math. Riemann, however, looked at integrals, and he devised a tactic for calculating the area exactly under a curve, and it's called well, named after him, his namesake, Riemann sums. And his scheme was this. His scheme is to imagine taking the area under a curve, and instead of instead of looking at this as a whole big thing, he looked at ways to estimate the area. And he thought of two different estimates. One is called the lower sum, which works as follows. He looks at subdividing the area under this curve into a bunch of rectangles. So thinks of subdividing it into a bunch of rectangles. So I'm going to divide it into this, however many rectangles this is. And he looked at the lower sum is gotten by creating a rectangle whose height is the minimum value that the function is in each of these intervals. So this is the first interval, and this is the second. So he devised, you've got a rectangle, and it looks like the minimum value is at this initial point. And it looks like the minimum value of this next interval is somewhere in here. And it looks like here. And then like the minimum value might be something like this. And then it looks like the minimum value is somewhere in here. And then it looks like here. And Riemann said, this is one way to estimate the area under the curve using a sum, using these lower sums. We're choosing the output that's the minimum in each of those intervals. And using summation notation, it looks something like this. What's the width of every one of these? Since the area of a rectangle is length times width, the area of every one of these rectangles, if you subdivide them evenly, is just the length of this full interval, so b minus a, divided by how many intervals there are. And we'll say that there are n of these intervals. So this represents the width of each interval. The height of each of these is just the function evaluated at this special point. Riemann called it x star, and the star just represents it's a special point. And what is this special point? Well, for the lower sum, it's just the output that's the minimum in that interval. And so what Riemann says, if you take this width times this height, you get the area of one of these rectangles. If you do this for every one of the rectangles and then add them together, you'll get an estimate for a lower bound of the area under this curve. So he decided, let's add all these rectangles together. We'll let k equals 1 to n, and we'll say this x sub k, this is just the x value in that interval. So in this case, it looks like k goes to 6. 1, 2, 3, 4, 5, 6. And Riemann called this his lower sum of n rectangles. Okay, and again, where x star of k is the minimum, is the x that goes on with the minimum in the interval x of k minus 1 all the way to x of k. He did the same thing with the upper bound. So instead of doing minimums, you could do maximums. So you could do maximums. You could do an upper sum. So maybe I'll look at an overestimate of all these, where we do exactly the same, just now the x star corresponds to the maximum in this interval. So you could say that maybe u sub n is an upper sum, where the widths are still the same. And the notation still looks the same because the star still represents a special x, but this time the specialness is the maximum value that the function takes in any given interval. And if you sum these together for every one of these, you get an upper estimate on the area that's underneath of this curve. Same bounds for x star. And what Riemann said is that as you make these estimates finer and finer, as you subdivide this smaller and smaller into thinner and thinner rectangles, that the sizes of the upper rectangles and the lower rectangles become closer and closer to each other. In fact, they become arbitrarily close. So if you look at the limit so Riemann says that if you look at the limit as n approaches infinity, as you subdivide these smaller and smaller and smaller, that the difference in size between the lower estimate and the upper estimate becomes 0. And since it becomes 0, it becomes the exact area under the curve. So I'll write that down. So let f of x be, and this applies to continuous functions on a closed interval on AB. Then we say that the exact area, or the definite integral from a to b of this function, sometimes known in this scheme as the Riemann integral from a to b, is each of these sums of f of x k star, that each of these sums become closer and closer to the exact area as you let the number of rectangles approach infinity. So the width of the rectangle becomes like the dx, like delta x, and then the sums of the heights become the outputs of the integral. So this is the process, the underlying estimation process that we use to find the areas to find the values of definite integrals. Note that this scheme does have some limitations in that this only really works for continuous functions. It doesn't work if the domain is kind of badly behaves with the range. It's got some real limitations, and in fact, if you move on to study calculus at a much higher level, there are other schemes for computing integrals. One of the most famous alternative is known as the Lebesgue integral, which we will not be studying in this class, but it's out there to think about and to look at that allows you to calculate integrals that you can't really with this Riemann scheme. For us, what you need to know about this is that you need to know what the definition of this is, and you should be able to use this definition to show some properties of the definite integral that we know. So, for example, here's one that if you want to find the integral from a to b, you could find the limit from a to some middle ground c, and then add that with that same middle ground to the other endpoint b. And this is true for any c that's somewhere in the middle of a and b. So I hope this intuitively makes sense. This is like saying the area of the whole thing is equal to the sum of the non-overlapping parts of the area. Intuitively and geometrically, I hope it makes sense. Let's make use of this definition of the Riemann integral to show that it does make sense and to show that it does work. So note that by definition, this limit from this integral from a to b of f of x, the definition is this. It's the limit as n approaches infinity of b minus a over n times the sum of k equals 1 to n of f of x star of k sum. So this integral is really a sum. What can we do? We want to somehow break this into sums that have c's in them. I'd like to get a c in here, and we're going to use our classic and now kind of well-worn trick of if I want to force something to be in an expression. One way I can do that without changing the value is both add and subtract it. So I'm going to force it into the numerator up here because that's where the a's and b's are already. So I'd like a c in there somehow to be able to manipulate this. Limit as n tends to infinity of, I'm going to do, how about b and then subtract c and add c in the middle. And then we're still subtracting a. And then we have the same sum. What does this do? Well, by doing this, we can split this big fraction into two individual fractions. If we want to be real precise, which we should be. We split this into b minus c over n plus c minus a over n times the sum. We can distribute the summation to each of these two fractions, and then the limit of a sum is the sum of the limits. So then I can distribute this guy in and then split this into two limits. I can split this into two limits. The limit is n tends to infinity of b minus c over n times our sum, k equals 1 to n of f of x k star, plus the same limit, this is c, of c minus a for n times that sum. And I won't bother filling it in because it's the same. So what are these? Well, these are just the definition of a definite integral. This is the definition of a definite integral with limits of b and c instead of b and a. So note this is the integral from b to c of f of x dx. And this is, again, has the same structure as our Riemann integral, just now c is playing the role of b. So the upper limit is c and the lower limit is b. Excuse me, is a. And voila, we've arrived at our conclusion.